So hello everyone. Welcome to the live section of this course, which is Wave Optics. So I'm Gitanjali. I'm a PhD scholar from IIT Delhi and I'm the TA for this course. So now we are in week 5, where we have seen two of the most important optical interferometer of wave optics, which is Michelson interferometer and Fabry-Perot interferometer. So we'll see in details what are the working principle of these two types of interferometer. Then we'll start solving some problems of week 5. So before starting the session, let me just know whether my voice is it clear to you and whether the screen is also visible to you. Okay. So let us start then. So these two types of interferometer, these are based on the division of amplitude. So based on the division of amplitude, we'll see interference pattern on the screen. So if you look at this figure, this is one of the figure I took from Wikipedia. So this is the schematic of the Michelson interferometer. So if you see the left side, so here we have this is the schematic of the Michelson interferometer. So here I have two types of mirror, two kinds of mirror. One is M1, other one is M2, and we have a beam splitter which is present in the middle of this Michelson interferometer. Then we are observing the resultant pattern that can happen after passing through this beam splitter in this detector position. So what we do, we incident the light when the light from this coherent source, when it hits the beam splitter at the point C, then the beam splitter, what it will do. So these are usually coated with silver so that part of the light will get reflected and part of the light will get transmitted through it. So you can see that some of the light will get reflected towards the point A and some of the light will get transmitted towards the point B. And from the mirror, they will again get reflected towards this beam splitter. Also from the point A, it will get reflected to the beam splitter position. So when these two types of beam, when they meet at this beam splitter, then it will interfere and we'll see the interference pattern on the detector position. So in the right side, this is what we see in the experiment, the circular alternative bright and dark fringe in this Michelson interferometer. So this is from sodium lamp source. Here we can see we have a bright spot at the middle, then we have dark ring, then bright, then dark, bright, dark, and this continues. So, and the contrast between this interference fringes also up to what length you can clearly see the fringes. It all depends on what is the kind of source you are using, what is its spectral purity, which we determine using the coherence length. So depending on the coherence length, we'll see uh, bright contrast, and if the coherence length is much smaller, then the contrast won't be that much. Okay. So to see the condition of this bright and darkening, so what we have done, we have taken the equivalent optics model to calculate what is the net part difference. So the net part difference, it is nothing but the combination of delta P plus delta R. So delta P, it is the geometrical part difference because of this mirror position. And delta R, it is the part difference because of the reflection from the Can you get a dark spot at the center? So yes, it's not like you will see a bright spot at the middle. So it all depends on the positioning, relative position of M1 and M2. What is the separation between them? So if you change the separation between the M1 and M2, then the central fringe, whatever you got at the center, it will change. Okay, you may get dark, you may get bright fringe. It all depends on what is the separation between M1 and M2. To see that what is the condition to get this bright fringe at the middle or dark fringe at the middle. So we need to look at what is the power difference in this experimental setup. So in brief, what I can say is that the beam splitter that is present in the middle. So what it will do is that, so you can see it from here that we are observing the fringes in this direction. So here it is, here we are observing the fringes. So what is the fringes that we'll get using this Michelson interferometer? So what this beam splitter is doing is that it creates a virtual image of M2 in the direction of this detector. So it creates a virtual image M2 prime here. Let's say this distance is x1, this distance is x2. So that means from this position, this will be x2. Okay, so the separation between this two mirrors M1 and M2 prime, this is D, which is x2 minus x1. So this is the linear optic equivalent to, this is nothing but the mathematical representation of the experimental setup to calculate what is the fringe patterns and what is the condition of uh, constructive and destructive interference. So from this linear optic model, we see that the delta P, which is the geometrical part difference, this is 2D. Actually, it is 2 and D cos theta, but mostly we take that this is the air, so that is why n is 1. And the part difference due to the reflection, this is lambda by 2, which correspond to a phase difference of pi. So this is the net part difference. Now to get dark ring or dark fringe, the net part difference, it should be equal to the usual condition, which is m plus half lambda. And for bright fringe, we need to have the part difference. It should be m lambda. So m is starting from 0, 1, 2, 3. Okay. So if you put the value of, if you simplify this condition, put 2d cos theta and lambda by 2. So we see that for dark fringe, it should satisfy 2d cos theta is equal to m lambda. Theta is the angular position of this ring. So where this ring, where at what angle you are getting this ring, different types of ring. Okay. And D is the separation between the mirror M1 and M2. So similarly for bright fringe, we will get 2d cos theta should be m minus half lambda, or you can take, or let's take m plus. It can be m plus half lambda also. These are only conventions used in different textbooks. Okay, so for dark fringe, we need to satisfy this condition, and for the bright fringe, they need to satisfy this condition. So let us say we are seeing a dark fringe at the middle of this Michelson interferometer. And for the center point, so we can, for the center spot, so the ray is incidentting directly on this detector. So that means theta, it is 0. So we can take cos theta is 1. So that means for central spot, the condition is 2D should be equal to m lambda. Okay. And this m, it is the maximum value of m that is present that we can get in the experiment. So all the rings that is there beyond this dark fringe, they have values, they have m values that is lesser than this m max value. So to see that, so if you know the value of d during experiment, you can calculate the value of d, and the lambda value is also known to you. So we can easily calculate what is the maximum value of lambda, which is 2d by lambda. And for other dark fringe, which is beyond this central fringe, so they should satisfy 2d cos theta is m lambda. So if you use these two and if you subtract these two, then we can easily get a relation which is 2d 1 minus cos theta should be m max minus m lambda, which we take p lambda. So p is the in experiment we say it is what is the number of fringe. So don't count the central fringe as a one. So except this central fringe, central dark fringe. This is the first dark fringe. This is the second dark fringe. This is the third dark fringe. So don't count the central one. Okay. So this is for the condition of constructive and destructive interference. So now if you vary the value of D, what will happen experimentally that these fringes that we have here, the circular fringes, they start to collapse. If you decrease D, then they start to collapse toward the center. So to know what are and using this experimental observation, you can calculate what is the wavelength of light that you are using during the experiment. So to get the wavelength, we can use the 2D equal to m lambda. And from this, we can differentiate it to delta D should be to delta lambda. So from this, sorry, the order is changing, so lambda is constant. So wavelength we can calculate is this is 2 delta D over delta M. So this is the delta D, it is the shift or the change in the mirror position. Delta M, it is the number of fringes that collapse because of this change in delta D. So using this relation, you can easily calculate the wavelength during the experiment. Okay. So I think this is about the Michelson part, Michelson interferometer. So one thing that is that, as I said, the contrast between the fringes, it all depends on the coherence length. So if the coherence length is small, then we need to have the part difference that should be in the order of the coherence length so that we can see the fringe pattern on the screen. So if you take a white light, so instead of laser, they are highly monochromatic and the spectral purity is also high and the coherence length is also high. So if you use a laser, so you will see high contrast fringe on this screen. But instead of laser, if you use a white light source. So what is the difference between these two types of sources? This is the only difference is that the coherence length. So laser have long coherence length and the white light source, they have short coherence length. So to see the fringe pattern on the screen, what we need to have is that whatever wavelength is there in the white light source, they should experience equal length while traveling through this M1 and M2 path. so that the power difference is zero and you can see the interference pattern on the screen. So to do that, one trick is to use the compensating plate. So this compensating plate, they are usually introduced to make this path length equal in M1 and M2 direction. And using this, we can see the interference pattern, but the contrast would be not as bright as the laser light. So if you compare the laser light with respect to the white light source, the laser light have high interference contrast as compared to the white light source. And another trick to get to see the interference fringe using the white light source is to use a square beam splitter instead of this rectangle beam splitter. So what it will do, it will create equal power difference. You can see that these ray, also these ray, they cover the equal path length in this beam splitter. So using these two types of trick, you can you will be able to see the interference pattern using the white light source. Okay. So this is some of the one of the additional information. So now let us move to our next part, which is the Fabry-Perot interferometer. So if you recall the Michelson interferometer, it is more and less like a two beam interference, but in Fabry-Perot interferometer, so it's also based on division of amplitude, but we'll see multiple beam interference in this Fabry-Perot interferometer. So in the experimental setup, what we have a light source and we you use a lens to direct this light source towards this two mirror arrangement. So we have M1 and M2. So this M1, it is perfectly reflecting. Experimentally, it is perfectly reflecting, and this M2, it is partially reflecting. So what will happen? Whatever light will get incident on this M1, it will get reflected. But for M2, whatever light will get incident, some part will get reflected and some part will get transmitted. Okay. And in the right hand side, we have another lens to converse this multiple beam towards this detector position. Okay. So using this, what we have seen, we have calculated what is the power difference and what is the condition of the constructive and destructive interference. Okay, so for that, what we have used, we have rotated the mirror. So we have two mirror. This is M2, this is M1. So light is getting incident, then it is going multiple reflection. So I hope whatever uh, mathematical uh, part that has been covered, it is clear to you. If not, let me know. I will try to cover it also. Okay. So what we have done in this part is that we have used the Stokes relation, and let's say this refractive index is NF, or let's say N2. This is N1. This is also N1. So when and we have taken that R and T. So these are the reflection coefficient when the wave travels or reflected from N1 to N2, and R prime, T prime. This is the reflection and transmission coefficient when the light is getting transmitted from N2 to N1 or getting reflected from N2 to towards N1. Okay. And we have used, let's say this is E0, then this will be TE0, and this will be RA0. So similarly, we have used the reflection and transmission coefficient to calculate what is the intensity of the reflected light and intensity of transmitted light. Okay. So what we have found is that IR is, this is the intensity of incident light multiplied by 2 R square 1 minus cos delta over 1 plus R2 R4 2 R square cos delta. So delta, it is nothing but the power difference between two consecutive reflected light, which is, if you recall, it is K0 delta or K0 2 into T cos of theta T. And also we have calculated what is the intensity of transmitted light. So this will be IA 1 minus R whole square 1 plus R to 4 2 R square cos of delta. So from this expression, you can see that the intensity depends on the power difference delta. So that means if you, let's say, if you want to have maximum of light getting reflected back. So for this, we need to have IR maximum. And this will be maximum when, if you see here, when it is cos of delta is -1, then this will be, the reflected light will be maximum. So cos of delta is -1. That means delta should be m plus half 2 pi. So that means the power difference would be equal to m plus half lambda. Okay. So this is to have the reflected light maximum. Now let's say we want to have the transmitted light maximum instead of the reflected rays. So then automatically the reflected light will be minimum. And this will be the case when cos of delta, it is 1. So that IR is 0. So IT will be maximum when cos of delta is 1. And this will be the case when delta is 2m pi, or the power difference is m lambda. Okay. So after deriving whatever condition required for this constructive and destructive interference, we have used the Stokes relation to express this intensity in terms of reflectance and the transmittance. Okay. So if you recall the Stokes relation, so this is nothing but R is minus of R prime and T prime is 1 minus R square. So using this, what we have calculated. So we have found out that we can express IT as T square 1 minus R square 1 by 1 plus F sine square delta by 2 intensity of incident light. F is the coefficient of fineness. So this is given by 4R 1 minus R square. R is the reflectivity of the error. Okay. So from this expression, you can easily calculate what is the maximum intensity of the transmitted light and what is the minimum intensity of the transmitted light. It all depends on this power difference delta. And this maximum and minimum intensity, if you recall, T max is t square 1 minus r square, and t minimum is t square 1 plus r square. Okay. And after that, what we have seen is that we have seen the resolving power of the Fabry-Perot interferometer. That is, how accurately this Fabry-Perot interferometer can be used to distinguish two wavelengths that have separation which is much less. So if two wavelengths are close to each other, then uh, how accurately this interferometer will able to resolve that. Okay. Uh, it's fine. Mm, it doesn't. If you are joining late, then it is also okay. Uh, uh, but if you have any doubt, let me know so that because I have covered some of the parts. So if you want me to go through it again, I will be able to do that. But let me know if you want me to cover that. Otherwise, you can go through the lecture after I upload the video file. Okay. So if you recall, so let's say we have a source that is that have more than two wavelength component. So if you recall the sodium source, they have two wavelengths that is close to that are the separation is quite low. So we say this is D1 and D2 line. So if this source have more than one wavelength, then depending on this constructive and destructive interference condition, each of this wavelength will produce its own interference pattern. So what we'll see in the screen is that we'll see rings. Sorry, my drawing is not that good. So let's say that we have two wavelength, then one of the wavelength will create fringe patterns, then other wavelength will also create its own fringe pattern. So in the screen, we'll see fringe pattern because of this two wavelengths. So to this, so we have lambda 1 is lambda. Give me 1 minute. And we have other wavelength, which is quite close to lambda 1 with a small wavelength gap, delta lambda. So the resolving power, by definition, we say this is delta tau by tau or delta lambda over lambda. And this resolving power, we use the Rayling's criteria to calculate what is the resolving power of this Fabry-Perot interferometer. And if we recall, this criteria is given by I min should be equal to 8 by pi square I max. And using some calculation, we have calculated R, the resolving power R, it is lambda over delta lambda or tau over delta tau. It should be 1.515 m root over m. Okay. So to accurately resolve to wavelength, it should satisfy, should have a minimum value of this. And from this, we can calculate what is the mirror separation between this M1 and M2 so that we can easily resolve this two wavelength. I think this is all about Michelson and Fabry-Perot interferometer. So we'll start solving few problems now. So before solving problems related to week 8, let us see two of the problem that we haven't solved from week 4. After that, we'll move to week 5. I think up to question number 18, we have solved it. Yes. So question number 19, we have in a Young's double slit experiment. S1 and S2 are, these are coherent sources, and S is the screen having a hole at a distance of 1 millimeter away from the central line. White light from 400 to 700 nanometer is sent through these slits, which wavelength passing through the hole has strong intensity. So this is the schematic. These are two slits and these are coherent. The separation is 0.5 mm, and in the screen we have a hole at a distance 1 meter from the center. So the question is asking, through this hole and within this wavelength range of 400 to 700 nanometer, which wavelength will have a strong intensity? I will give you some time to calculate. First, try to solve it first, then I will go through the solution. Recall the part difference for Young's double slit experiment. From that, try to find out the condition to get constructive interference at this whole point. Answer is C. Yes, it is correct. So to get strong intensity, that means to get constructive interference, What we need to have is the power difference, optical power difference. It should be integral multiple of lambda. So the power difference for Young's double slit experiment with no glass slit that is present in this mirror and the slit. So if there is a glass slit, then the power difference will change. But here we don't have that. So that means the power difference is A sin theta should be m lambda. Sin theta is y by d, which is m lambda. So the condition for constructive interference that we have seen earlier also, this is m lambda d by a. Or we want to find out the wavelength. So wavelength is ya over md. D is given, it is 50 centimeter. Y is also given, is 1 millimeter. So we put all this value. We have 0.5 m e minus 2. So in the range 400 to 700. So if you check it, then if you put the value of m is 2, then you find out that lambda is 500 nanometer. So for 500 nanometer, we will get the integer value of m. So that means we'll see a constructive interference at the screen. So the answer is option C. Okay, so the next question, and it is the last question for week 4. So in Newton's ring experiment, it is performed with a source of light having two wavelengths. Lambda 1 is 6 into 10 to the minus 5. Lambda 2 is 4.5 10 to the minus 5. It is found that the nth dark ring due to lambda 1 coincide with the n plus 1th dark ring due to lambda 2. If the radius of curvature of the curved surface is 90 centimeter, find the diameter of the nth dark ring for lambda 1. Try to calculate it first. Recall what is the diameter expression for the Newton's ring and equate the two of this diameter for nth for lambda 1 and n plus 1 for lambda 2. So from this you can easily calculate what is the value of n and what is the diameter for nth dark ring. 0.18 root 2. Okay, let me see. Let me go through the solution. I think the answer you are getting is correct. No, the ring is not given because it's okay. So you are asking about n. So n, I think it is, you will get 3 for this case. Let us see. So the expression for the diameter is, if you recall, so dn square is 4n or lambda 1. So d square n plus 1 is 4 n plus 1 or lambda 2. So these are equal. So that means it should be, so if you rearrange it, we'll get n is lambda 2, lambda 1 minus lambda 2. And the value of lambda 1 and lambda 2 is given. So these are the two values. So 4.5 into minus 5. So this will be 3. So that means the 4 in lambda 1 and the radius of curvature. So d3 is square root of this, which will come around 6.48. Which is, this is, I think, 0.18 into root. Okay, so these are the two questions for week 4. Let us see the problems related to week 5. So this is the first question. Find the wavelength of light using Michelson interferometer if 200 fringes cross the field of view when the movable mirror is moved by a distance of 0.0589 millimeter. So you are given the number of fringes that collapse from the field of view, and the mirror, the movable mirror, is moved by a distance of 0.0589. So for given this information, what is the wavelength of light that you are using in the Michelson interferometer? Let me know the answer. Yes, the answer is B. So you must have used lambda is 2 delta D over delta I. Delta D is given, which is 0.0589. millimeter and delta m is 200. So this will give 589012. Okay, so let us move to our next question. The question is, find the order of the central fringe, which is bright, and the angular radius of the 10th bright ring in a Michelson interferometer when the central part difference 2D is 1.5 mm. Assume that lambda is 600 nanometer. So first, let me know what is the order of the central fringe. Then you can calculate what is the angular radius of 10th bright fringe. So the given information is the central part difference today is 1.5 mm. Lambda, it is given 600 nanometer. You need to find the order of the central fringe. And for this, we need to calculate the value of theta. This is the value of m. Order is 2500. We also given it is bright. Central fringe is bright. So let us see. So if you recall of our Michelson interferometer or bright fringe, what is the condition we have? Should be 2D cos theta should be m plus half lambda. This is for bright fringe, and for dark fringe we have 2D cos theta is m lambda. So that means we can write m plus half is 2D cos theta over lambda. And for central fringe, the theta value is 0 because it is at the center, so angular degree is 0. So that means cos theta we can take it as a 1. And if we put it here, we have m plus half should be 2D over lambda. D value is given, or I think 2D is given 1.5 mm. 2 minus 3 and lambda is 600 nanometer. So this will give a value of 2500. But the order is M, which is M max for central fringe. This is 2500 minus 0.5. Angular radius is 5.13 degree. Okay, so let us calculate that also. So the main difference is that we need to consider the condition for this bright fringe. So the M value, if you take 2D cos theta equal lambda, then we'll get a value of this. But because it is a central fringe, we'll get a value of this. Now what we need to calculate is that the angular diameter of 10th bright fringe. So that means P is given, it is 10. So that means M is M max minus P, which will give a value of 2489.5. So that means to find out theta, so 2D cos theta is M plus half lambda, which will be 2490 lambda. So cos theta is 2490. Wavelength is 600. 2D is 1.5 into 10 to minus 3. So from here you will get theta is cos inverse this value, which will be around 5.126 degree. Yes, or 5.13 degree. Okay, so let us move to our next part. Question number 3. We have, it's given the initial and final readings of a Michelson interferometer screw are 10 point. This is the initial reading 10.7347 and another reading is 10.7057. And when 100 fringes pass through the field of view, calculate the wavelength of light used. We need to calculate what is the wavelength. Okay, option A. Yes, it is correct. So readings is given. This is the initial and final reading. So that means you can calculate what is the relative position of the two mirrors D, which is 10.7347 minus 10.7057. So this is delta D. So lambda is 2 delta D over delta M. So this will give 0.029 and 100, which will be 5800 angstrom. Okay, so let us move to our next question. Question number 4. Even circular fringes are observed in a Michelson interferometer illuminated with wavelength of 600 nanometer. When the distance between mirrors M1 and M2 is 0.3 centimeter, the central fringe is bright. Calculate the angular diameter of the seventh bright fringe. Distance between mirror is given. Lambda is 600. The central fringe is right. Need to calculate what is the angular diameter theta of the seventh bright fringe. Um, so whenever we say the angular diameter, so here the question says to find out theta. So whatever, I think you are getting theta 2.14 degree, if I'm not wrong. So this is the same answer. We need to calculate the theta value. So if there is a confusion between, I think, angular radius and diameter. There may be confusion that it may be, some may find this will be 2 theta. So it's, if that is the case, then let me rewrite it. So let us say this is radius. What I mean is the, some may find this is the solid angle. So you have a ring here. This is the solid angle, right? Let's say some are taking this is theta. Then maybe other will take this is also theta. So this is 2 theta. So this is not the case. The question is asking about the angular, the theta value. So what we have is here is that it's given the central fringe is bright and the distance is given, lambda is given. So we can calculate what is the maximum value of m. From that we can calculate the p value, and using the constructive interference condition we can calculate what is the value of theta. So for bright fringe, this is 2d is m plus half lambda. 2d is given, so that means m plus half is 2d over lambda, which is 10,000. Okay. Now for the seventh bright fringe, can take m is mx minus p. P is 7. Mx from here we can calculate it. This will be now for the 7th bright fringe, we can use 2d cos theta is m plus half lambda. Cos theta is m plus half lambda by 2d. So lambda by 2d we have calculated it. This is 10,000 and n plus half will be 9993. So n%. So that means theta is cos inverse 0.9993, which will be 2.14 degree. Okay, so answer is option A. So let us move to the next question. So the next question is also a easier one. So it's given it's a continuation of the previous question. So given what is the distance by which the movable mirror of the Michelson interferometer is moved if a shift of 200 fringes is observed. Option 1, yes, it is correct. So we need to calculate delta D. Delta M is given, lambda is also given, which is 600 nanometer. So delta D is delta M lambda by 2, which will be 200, 600 into minus 9 is 6 micrometer. Okay, let us see the part C. This is also a continuation of the previous question. So it's given when a thin film of a transparent material of refractive index 1.45 at wavelength 600 nanometer is inserted in one of the arms of the Michelson interferometer. A shift of 65 circular fringes is observed. Calculate the thickness of the film. So we are inserting a thin film of transparent material, which is refractive index 1.45 at wavelength 600 nanometer, which is the wavelength we are using for interference pattern also. And we are getting a shift of 65 fringes. And B, yes, it is correct. So, so when we insert a thin film of thickness T, so what is the optical power difference that will be introduced? So we have the new optical power difference, which will be created by thin film of thickness T. So this is OPD, which is mu minus 1 to T. So this is in A, but if you insert inside a Michelson interferometer, you can see that the ray travel twice between mirror M1 and M2. So it get reflected from M1, then again it is directed towards the beam circle. In between, we have a thin film of thickness T. So because of this dual travel, the net optical power difference is 2 times of mu minus 1 T. Okay, so this is nothing but 2 times delta T, which is delta M lambda. Okay, so delta M is given and we want to find out T. So that means T is delta M lambda 2 mu minus 1. Delta M is 65, is 600. 1.45 minus, which will have value 43.3 micrometer. Okay, so option B. Let us see our next question. Question number 5. Let me know if you have any doubt in between so that I can clarify at that point. So in question number 5, it's given a white light is incident normally on a Fabry-Perot interferometer with a plate separation of 4 micrometer. Calculate the wavelength for which there are interference maxima in the transmitted beam in the range between 400 to 500 nanometer. So you are incidentting white light on a Fabry-Perot interferometer, which is a plate separation of 4 micrometer. First, recall what is the condition for getting the interference maxima in the Fabry-Perot interferometer. Then you can use the value of M, different value of M, and check which of these lambda is satisfying the interference maxima condition. Yes, the condition is 2D is equal to M lambda. You can see here the wavelength is already given. So you can easily calculate what is the maximum value of M that you can get and what is the minimum value of M you can get. If you know the maximum and minimum value, then in between value you can easily calculate it. No need to check M equal to 1, 2, 3. First calculate what is the maximum value. Yes, the value of N can be varied from 16 to 20, both included. Yes, so I think you have easily guessed solution. So for to get the interference maxima in the transmitted beam, we need to have 2D should be equal to m lambda. That means m is 2D over lambda. Given this, we need to check between 400 to 500 nanometer. So let us first calculate what is the maximum value of lambda. Let us see whether 400 nanometer is also giving interference maximum. So when lambda is 400 nanometer, we have m is 2D over lambda. D is given 4 micrometer. So 4 into 10 to the minus 6 and 400 nanometer. So this will give 20. And for other extreme, which is lambda is 500 nanometer, m is d by lambda. So this will give value 16. Yes, the answers are correct. So we know the value of minimum value of m and what is the maximum value of m. So that means now we can easily calculate what is the value of lambda that will give the interference maxima in the transmitted. So for 16, it is 500. For 17, if you calculate it, it will give 470. And for 18, it will give 444. For 19, this will be 421.5. And for 20, it will be 400. So these are the wavelength that will give the interference maxima in this transmitted wave. So we'll move to our next problem. If here we have used sodium lead, then m is not an integer value as a calculator. What does that mean physically? So instead of white light, you are using sodium light. M is not integer value as I calculated. Okay, so the physical interpretation is, let me think first. So ideally the value of m should be integer. Okay, so one thing I can tell is that, so if you have a sodium source, or let's say you have a source which is more than 1 watt, so sometimes you will get values that are not integer value. So this happens because let's say this is for lambda. So this the interference for this, let's say you are getting a constructive interference or a bright ring or dark ring around this point angular diameter. So for this 2D cos theta is m1 lambda 1. For this 2D cos theta is m2 lambda 2. So what happens is that the value of m1 for this is not equal to m2 for this. Okay. So sometimes what will happen if the value for m1 is, if you want to express m2 in terms of m1, then you may find that this is m1 times some multiple of 0.5. What I mean is that the order for these two rings are, they are not in, even though m2 is a integer, but if you express in terms of m1, then you find it that this is some multiple of m1 plus some multiple of 0.5. So physically what it means is that uh, so mathematically, it means they have the value for m1 and m2 are integer for both the cases. But because you are expressing one order in terms of another order, you are getting a value of 0.5. But physically, it means um, I'm not able to interpret what does it will mean physically. Okay, so for now, is the mathematical explanation is okay with you? We'll see in detail what does it mean physically. Maybe then light won't be transmitted in normal. Yes, yes, you're correct. So if you see this is for M1 today cos theta is M1 lambda 1. For this case, M2, even though it is an integer, you are expressing in terms of M1 plus 0.5 times of N. So that means for this case, you will get a bright fringe, sorry, dark ring. We are considering Fabry-Perot, right? Yes. So this will be bright ring. And this will give a dark ring. So that means it will cancel with each other. If these are close, then they will cancel. But even though, let me check it again if the explanation is correct or not. Okay. Let me know what are the observation you are also getting while the experiment. Ideally, what happen is that uh, we will experimentally will change the value of d, and we'll see this separation getting changed, and in some of the cases for d we'll see that they will overlap, so the interference pattern will vanish. Then after some point, if you again change d, then you will see again this interference pattern will reappear. So let me know what are the observation you will get. So for now, let us move to our next question. So the question is asking, calculate the resolving power of a Fabry-Perot interferometer made up of reflecting surfaces of reflectivity 0.85. And these are separated by a distance of 1 mm at lambda 488 nanometer. So given this information, you need to calculate what is the resolving power. Try to recall what is the expression for this, the resolving power. Then we'll get to know what is the answer for this. Seven point nine 10 to 4. That means you are getting a value close to this. Yes, option A is the correct answer. So resolving power, it is lambda by delta lambda, and we have found the expression 1.515 m square root. And so for that we need to calculate f. F is 4r 1 minus r square. R is given 0.85, which will be 151. So lambda by delta lambda. M we can write it as 2d by lambda square root 151. So d is also given 2d, which is 2 into 10 to the minus 3. Wavelength is 488, which will be 7.63 into 10 to the 4. Okay. So let us move to question number 7. It's given two Fabry-Perot interferometer have equal plate separation, but reflectivity of one is 0.8 and another one is 0.9. What is the ratio of full width at half maximum of the transmission peaks? R1 is given 0.8, R2 is given 0.9. So you need to find out the ratio of full width at half maxima of one with respect to two. Recall the expression for full width at half maximum. Option B. Yes, it's correct. So full width at half maxima, it is given by 4 by root over of f. This is the approximate value if you have high value of f. So we can use it for our calculation. So that means if you calculate for first one, which would be 2, 1 minus r1 square root of r. R1 is given, it is 0.8, and if you put the 0.8 value, you will get around 0.45. And for second one, you can follow a similar step. So this will be 2 1 minus r2 square root r2, which would be 0.211. The ratio would give a value of 2.133. Okay, so let us move to our next question then. So we have, this is for the Michelson interferometer. Circular fringes are obtained with a Michelson interferometer using wavelength 600 nanometer laser light. What minimum displacement of one mirror will make the central fringe from bright to dark? Option A 600, B 300, C 150, D 120 angstrom. Just recall the condition for the bright and dark pattern at the central point. So if you compare that, you can easily calculate what is the minimum displacement of one mirror with respect to the other, so that you can get bright to dark. Option C. Yes, it's correct. So the minimum separation would be, minimum displacements would be 150. So the way to find out the answer is that given initially the central fringe was bright. So that means you have 2d1 is m plus half lambda. Now let us say you are changing d by some delta d, either plus or minus delta d, that we don't know. But let us say this is delta d we are changing. So that means now we after the changing we'll see a dark fringe. So that means this new d will satisfy m lambda. So this would be d1 plus delta d. So 2d1 we can use this here. So this is n plus lambda. So delta d is m lambda. So if you rearrange it, you will get 2 delta is minus lambda by 2, or delta d is minus lambda by 4. The value of lambda is given, it is 600 by 4, that means 150 nanometer. So that means the answer is saying you need to decrease the separation by a distance 150 to change the central fringe from bright to dark. Okay. So is the solution clear to you? Let me know if you have any doubt in any of these steps. So for now, let us see question number 9. In a Michelson interferometer, when one of the arm is moved away from the equal path length position by a distance of 5 centimeter, the fringes disappear. What is the coherence time of the source illuminating the interferometer? Option A 3.33 into 10 to the minus 10 second. Option B 2.82 into 10 to the minus 8 second. Option C 1.05 into 10 to the minus 6 second. Or option D none of them. So you are given in a Michelson interferometer, you are changing one of the mirror position away from the equal path length by a distance of 5 centimeter. And you are saying that by this movement, the fringes are getting disappeared. What is the coherence time of source illuminating the interferometer? So by equal path length position, what I mean is that the mirror's position M1 and M2, they are equal from this beam splitter position. X1 and X2 are equal. And now you are changing one of the mirror position and you are saying the fringe is visible. Okay, option A. Yes, this is the right answer. So option A is the answer. Okay. So the clue is that you are saying the fringe, you are saying that you are moving by distance this much and the fringes are getting disappeared. And the fringe will disappear only when the path difference is in the order of or it is equal to the coherence length of this length. So when it matches the coherence length, then the phase will vary rapidly and you won't see any interference pattern on the screen. So to calculate that, we need to calculate the total path difference. And if we recall, the total path difference is 2 times of the distance the mirror is displaced from this equal path difference, which is 5 into 10 to the minus 2. So this will be 0.1 meter. So that means we have the coherence length LC is 0.1 meter. So we know the coherence length. So coherence time is LC by C. So 0.1 over 3 into 10 to the power 8, which would be 3.33 to 10 to the minus 10 second. Okay. So let us move to our next question. So it's a conceptual one. It's given in a Fabry-Perot interferometer. The mirror reflectivity R is increased from 0.8 to 0.98, keeping the plate separation D fixed. Which of the following correctly describes the change in transmission spectrum? Option A, the spacing between successive transmission peaks decreases and the peaks get narrower. Option B, the free spectral range is unchanged and the transmission peaks becomes much narrower while their positions stay the same. Option C, the free spectral range is unchanged, but the peaks broaden because more light is reflected back and forth. Option D, both the free spectral range and the peak width increases. So you are increasing the reflectivity of the mirrors from zero point 0.8 to 0.98 by keeping all the other parameter constant. So what is the effect on the free spectral range and the transmission peak? Whether the free spectral range will get shorter or get broader, or the peak will get broader or narrower. Yes, the answer is option B. So the free spectral range, it doesn't depend on, if you recall, it is given by 4 by, uh, it is, I think, 2 pi. So it doesn't depend on the reflectivity of the mirror. So it will get unchanged. But when you change the reflectivity, so the R will change. So if you recall full width at half maximum, it is inversely proportional to F. So when we increase R, so the F will increase. So that means the full width at half maxima will decrease. So that means the peaks will get narrower when we increase the reflectivity. And this we have seen in the lecture also using some example. So you will get narrow peak at the same position. On the other hand, if you decrease the reflectivity, you will see broader peaks, the same position. Okay. So let us see question number 11. So it's given in a Michelson interferometer experiment. It's performed with a source of light having two wavelengths. One is 4882 angstrom and another one is 4886 angstrom. Through what distance does the mirror have to be moved between two positions of the disappearance of the fringes? So you have a source and it has two wavelengths. One is lambda 1 is 4882, lambda 2 is 4886. So it is asking that you are seeing disappearance of fringes between two positions. So for that, to see that, what is the distance between the mirrors that have to be moved to see disappearance of successive fringes? So as I said before, when you have two wavelength, what will happen during the experiment? You will see, sometime you will see distinct interference pattern, and after sometimes you will see there is no, the interference pattern is not there. And after some time you will again see the interference pattern. So the question is asking about what is the distance traveled by this mirror when you are seeing this observation. Yes, option is the answer to this. So the way to calculate it is that, so what is the thing that we are noticing, that we need to notice that there is no fringe on the screen when you have two wavelengths, lambda 1 and lambda 2. And it will only happen when one of the maxima of lambda 1 it overlap with the minima of lambda 2, or the maxima of lambda 2 overlap with the minima of lambda 1. So if it is the case, then destructive interference will happen and we won't see any interference pattern on the screen. So that means we need to take maxima condition for one and the minima condition for the two, for the second wavelength. So for this, we have, let's say we are taking the center fringe. So we are seeing maxima for one and minima for the second. From this, you can calculate. This would be lambda 2. So when you take the difference, this would be d over lambda 1 is up. So this is one of the expression that we have. Now we are changing d so that we can get the next condition where we'll see again the disappearance of fringes. Let's say we are changing the d by d plus delta d. So for this case, we will again have d plus delta d, lambda 1, d plus del lambda 2. The next part difference that we will see for this case is 3 by 2. So we can rearrange it. So this value is half. So that means this will give 1. So lambda 1 and lambda 2 is given. So we can easily calculate what is the value of delta that we wanted to find out. So this is the final expression, okay, in terms of lambda 1 and lambda 2. So lambda 1, lambda 2 is given. We just need to put the values. 8 2 10 to minus 10 divided by 8, which will be 0.298 millimeter. Okay. So this is for the disappearance of fringes. The condition that we have is that 2d by lambda 1, 2d by lambda 2 should be half, 3 by 2, 5 by 2, 7 by 2. So if we are seeing a condition like this, you will see no interference pattern on the screen. But instead, if you have 2d by lambda 1, lambda 2 is 1, 2, 3. So in this case, the maxima of one overlap with the maxima with the other. So in this case, we will see the fringe on the screen. Okay. So I hope the solution is clear. Question number, let us move to question number 12. So it's given calculate the minimum spacing between plates of a Fabry-Perot interferometer, which would resolve two lines with delta lambda 0.01 and lambda 600 nanometer. Assume that the reflectivity is 0.8. So what is the minimum separation between the plates so that you can resolve wavelength, which is separated by 0.01 mm, sorry, 0.01 nanometer, and given that reflectivity is 0.8. So what is D? Calculate it first and let me know the answer. Let me know the answer of this in millimeter. Okay. No need to hurry. Take your time and let me know the answer. One point two. Wait. It's quite close. So I think you have used resolving power. It is equal to 1.515 2d over lambda square root of f. So R value is given, you can calculate f. This will come out as, I think, 4 root 5. So to put 600. The value of D is, we want to calculate it. And this is 4 root 5. So if you rearrange it, I think you will get a value which is 1.32. So based on the decimal position, this value will vary. Okay, so let us move to question number 30. So it's given the student measures the Fabry-Perot interferometer transmission spectra and finds that the free spectral range to be 10 GHz and the full width of maxima for each transmission peak is 0.2 GHz. Find the fineness and the mirror reflectivity of the Fabry-Perot interferometer. So first let me know the value of f. Given this information, 1.575. This is 515, not 575. It may look like it is 575. So this is 1.515. So this way, if you recall the calculation of the resolving power, so this is the constant factor that we have found after the simplification. So if I recall, So let me check it. I think these are the constant pi's. Some pi square value were also included for this. So this is the constant factor that we got during the calculation. It was around 2 pi by 4.1. So, okay. Any other doubt? So we have used to calculate this 1.515, we have used Rayling's criteria to calculate the uh, resolving power. So we have used that, and after solving this Rayleigh criteria, we have found this constant factor of 1.515. Okay, if you don't have any doubt, can you let me know the answer for this? What is the fineness? Fineness is 50. Yes, you are correct. Uh, if you recall one of the formula for F, it is given by what is FSR and what is the full width at mix. And this is already given is 10 over 0.2. So this will be 50. So the next part is to calculate what is the mirror reflectivity. So for that, what we can do is, this is coefficient of fineness, right? Fineness symbol is, I think this. Okay. So from this, we know that we can relate it to coefficient of fineness, which is pi by 2 root f, or pi by 2 root r 1 minus r. So we have pi root r 1 minus r. So in the left hand side we have 50, and here we have this. So what to solve it, what we can do is that, so we can substitute as, let's say root r is x. So that means this is, we'll get 50 x squared as pi x minus 50 is 0. So this is the polynomial equation. You can easily solve it. So the answer is x is minus pi plus or minus root over of pi square minus, which is plus by 2. So we will get 0.969, and the value of r is square of x, which is 0. Approximately it will be 0.9. Yes, your answer is correct. You will get 0.939. So I have just rounded. Okay, so I think we can solve one more question. So it's a conceptual one. It's given in a mercury vapor lamp. An electric arc passing through the vapor produces light. When lamp is switched on, the arc is struck and the liquid mercury starts to evaporate as the temperature gradually increases. In a certain experiment, A Michelson interferometer is set off with a mercury vapor lamp as the light source and the lamp is switched on. Which of the following effect will be absorbed? Option A. Initially, the fringes will appear with high contrast but low intensity, which will be reduced in contrast over the period of time as the light builds up. Option B, initially no fringe will be absorbed, but then fringes emerge with high contrast as the lamp heats up. Option C, no fringes will be absorbed as the source is incoherent as has many frequencies. Option D, high contrast fringes will appear as soon as the lamp is switched on and will remain thus so as long as the lamp is on. So you are using a mercury vapor lamp, and what is the initial observation that you will see? Yes, option A is the correct answer. So the what is the explanation that you found to get the answer? Why you're thinking option A is the right answer? So the answer is it's like when you are switching on the mercury vapor lamp. So initially, uh, uh, during the initial stage, you have few mercury atoms that are evaporated. So because of this, you will see that the light that is emitted, they won't have that much broadening because in that case, when you have few atoms, the collision is less. So the coherence length will be large. So the light will have narrow spectral width. So we will see high contrast fringe pattern. But once the process continues, more and more atom will start to evaporate. So now we will have more atom in a closed space. So the collision will increase. So because of the collision, whatever the light is getting emitted, so they will have broadening. So because of the broadening, the coherence length will now decrease. So and because of that, we'll see that the contrast will now decrease. Okay. So initially the fringes will appear high contrast, but as it goes on, the contrast will decrease. Yes, your explanation is also correct. Okay, so I think we are done for today. So we'll meet on next Tuesday to see what is there in week 6 and solve problems related to week 6. So thank you for joining the session. I hope the questions are clear to you and the steps are clear to you, and also it will helpful to you to solve the assignment. Okay. If you have any doubt, feel free to ask me during the live session, or you can write it on this Google group also. So we'll meet on next Tuesday, same time from 6 to 8 to see what is there in week 7. Okay, week 6. So thank you everyone. So let us end for today.